right? I thought there'd be data. Is anyone out there?
Okay, let's get going. Welcome back. So you have a homework out. I just posted an announcement about a typo that is fixed. So if you're just looking at the homework online, you won't see the typo. And that was on 4A. There should be a 6 in front of that PDF. But I do want to say a few things about the rest of the homework just briefly. So number one is to find the distribution of a minimum of Pareto random variables, and that's a straightforward problem. I'm not saying it's easy or hard, it's just straightforward, nothing tricky. Same with number two, pretty straightforward. That's where you're finding the distribution of a maximum. And then we get into 3, where we're starting to look at more order statistics than just one. And so in 3, you're deriving the joint PDF for the minimum and the maximum. And I did want to tell you where that it said, well, it gives you a hint. And I wanted to tell you why that's true and where that came from. So for homework 3, number 3, you're supposed to get the joint PDF for the minimum and maximum of a sample. And so the problem takes a long time explaining that a joint PDF can be gotten by taking 2 derivatives of a joint CDF, and it defines the joint CDF. And so you really want the probability that x1 with parentheses, the minimum, is less than or equal to, I used an x and a y. I thought it was less messy than having subscripts, but you can call it x1 and xn. And xn is less than or equal to some y. So those are the minimum and maximum in a sample of size n. And remember, the comma is and, like intersecting those events. And the random sample, the first thing you do in these kinds of problems is you try to figure out, you know things about the x's, you know their PDF and their CDF, so you try to figure out how to rewrite this in terms of the x's. But if you try to kind of look at a number line and say, here is x and here is y, and actually they don't even have to be that way. Y could be below x, and then if they're both down below that, that's still okay. And that's kind of one of several problems here. There's just so many ways that things can happen. So to have the minimum below x, you can have like your sample fall, I don't know, like this, and just so many ways that can happen. And you can't, I think, in an obvious way, figure out how to rewrite it in terms of the individual x's. So I wrote out this relationship, and I just wanted to make sure you know where it came from. So the probability that the maximum is less than or equal to y, I expanded this as the probability the maximum is less than or equal to y, and the minimum is less than or equal to x. So like this event or this event, the maximum is less than or equal to y, and the minimum is greater than x. Like those are 2 ways for it to happen, and those are disjoint events. And that OR is a union. So the OR is a union, and because they're disjoint, you get to pull those apart, because when in doubt, go back to Venn diagrams. So if you're trying to find the probability of, so if this is a set A and this is a set B, and you think of probability as area, and you think of the total area of this rectangle as 1, then the probability of A union B happening would be given by the total area in here. And the probability that A union B happens is the probability that A happens. So think of it as area and look at the picture, plus the probability that B happens. And if you think of those as the 2 areas of the circles, you have overcounted the intersecting part. So you need to take that out. But of course, if they're disjoint, then there is no intersecting part. So if A and B are disjoint, then I can get just this piece. And so that's what I'm trying to say up here. The 2 things in brackets are like my A and B. And the point is that I've got the probability that the maximum is less than or equal to y is equal to the probability So then I rewrote things so they looked a little nicer, but the basic thing is that I turned that or into a plus. And then over here, I had two things, the minimum less than or equal to x, and the maximum less than or equal to y. And over here, the minimum greater than x, and the maximum less than or equal to y. So this here is the thing we want to solve for and then take the derivative of. And you already know how to write down this one on the left. It's just like any other max problem. And the reason I wrote it this way is this other term over on the right is easy to envision in terms of all of the x's, which is usually the trick. You're like, what does this mean for all of the x's? So just looking at this term, I would just start off by saying, okay, so assume x is less than y. Otherwise, yeah, this probability is going to be 0. So you don't even have to assume it if you want. You can say the case when x is less than y, you get 0. But if you draw like an x and a y on a number line, you want a sample to fall in some way that the minimum is above x and the maximum is below y, and that means they're all in between. So the probability that we're trying to find over here with the kind of usual goal of rewriting it in terms of the individual x's is the same thing as saying x1 is between x and y. The equals part doesn't matter for these continuous things. And x2 is between x and y. And out through xn is between x and y. And those are all independent random variables, so you can break that up into a product. And you are well on your way. And you can write each one of those terms as in terms of a CDF. And they're actually all the same probabilities because of identicalness. Okay, I wanted to give you a hint on 7. 7 is going to be really important to us. I pick most of these problems because we're going to need these results later. So they're not just kind of busy work. And 7 is going to be particularly important. In 7, you want to find a distribution of something. And in the problem, you're given that a certain function is invertible, but not necessarily differentiable, which if you try to go the G inverse transformation route, you're in trouble without having that differentiability. So we have x1 through xn. Are they IID? Yeah, they're a random sample, so they're actually IID from a distribution with CDF capital F, or you might call it capital F sub x. And in part A, you want to find the distribution of this yi, which was defined as capital F of xi. Just kind of weird. You're putting a random variable into a function, and that's just making another random variable. So my hint that I wanted to give you is I would go for the CDF of y, or yi. You can already tell at this point that the y's are going to be IID because each one comes from an independent and identically distributed x. So this function is not introducing any kind of dependence because we're not putting two x's together in one function. So the y's are going to be IID. And so I would start off by saying the probability that yi is less than or equal to some y is the probability that f of some xi is less than or equal to y. And then the CDF is invertible. Now all CDFs are non-decreasing, which means they're either increasing or they can be flat. But if it's invertible, it can't be flat. So this is strictly increasing. And therefore the inverse is strictly increasing. So you can take the inverse on both sides of this and not mess with the ordering. It's going to be an equivalent event. So this is the probability that xi is less than or equal to f inverse of y. But this is going to be the CDF for x evaluated at that thing. I won't write it anymore. Clearly there's some cancellation there. But in terms of recognizing the distribution, you should also go back and look at the original definition for the yi. It's defined through a CDF, which means it's a probability. So from this, you know that yi lives on 0 to 1. So that will also help you in the end down here. in identifying the distribution. And so once you know that, it has a nice name, then part B is a combination of the G-inverse method to get the distribution of a term, and then our moment generating function approach for getting the distribution of a big fat sum. And because moment generating functions are not the point of the problem, you can definitely just grab them off a table. You don't have to compute them. All right, so let's get started for today. I'm pretty excited about this. It's not the UMVU, which is the uniformly minimum variance unbiased estimator, the greatest estimator in all the land. That's coming up closer to Thanksgiving. But we're going to start talking about estimation, which is really the math stat now. So this deserves a whole new board of its own. We are in chapter 2, if you're following the notes, and I don't remember what I called this. Maybe qualities of estimators or something. So I'm not going to write anything here, but specifically we're in section 2.1. I think that has the title qualities, or maybe this was the chapter, I don't know. Qualities of estimators, good, better, and best. Okay, this is why you're here. Well, I don't know if you know why you're here, but this is why people who definitely want mathematical statistics and didn't just think it looked interesting do mathematical statistics. To estimate parameters of PDFs like the ones we've seen. So suppose that I have an exponential distribution number generator out in the hallway, and it has some lambda, and I'm not going to tell you what it is, but I bring in numbers that my generator is generating. We've already talked about this a little bit. You know, if you started kind of looking at these numbers, they're going to be really much more piled up down by 0. Because if you made a histogram of them and you had enough data to make a nice histogram, it should match the exponential PDF, which starts at lambda and goes down. So this curve is lambda e to the minus lambda x. So the data are the x's I wrote down there, and I'm going to bring them in, and I want you to tell me what lambda was. You can't tell me exactly, but based on this sample, you can maybe come up with an estimate. And what is a good way to estimate lambda? So you could potentially make a histogram out of your data and then try to figure out the height. This would be kind of weird because reasons, but you can figure out the height of your highest rectangle over here and say, I think lambda is approximately that. The reason that's a little weird is because it's totally dependent on how you bend your histogram, right? If you bend it narrower, the left rectangle is going to start shooting up, and then eventually you'll have nothing there, because if you bend it so narrow, your sample won't see any values there. So that's not even going to look exponential anymore. So that's one idea. Another idea is, so let me make this a little more formal. So I have x1 through xn, IID exponential rate lambda. And we want to estimate lambda. So that is the goal. We do know the mean of this distribution. The expected value of any one of these is 1 over lambda. That's a probability weighted average. But once we have the random sample, we could compute the average of those guys. And that would be called the sample mean, which is going to be a really important statistic for us throughout this course. The statistic being any number you can compute from data. So the sample mean we write as, and this should be nice and capital, x bar, and it's the average of your sample. So 1 over n, the sum as I goes from 1 to n of xi. And this is a random variable until you actually observe the data, and then you can get a number, right? So this is a random variable, and then you can observe like a little x1, little x2, so these are supposed to be actual numbers, and then you can get a little x bar, which is 1 over n, the sum of the little xi. So this is already probability weighted as well, because the sample are the x's on the picture I drew to the left, and they're going to naturally come out more clustered towards 0. So they're already weighted on their own. My point is that if you want to estimate lambda, you could say, I want that to be that color. If you want to estimate lambda, you can say, I know the mean or expected value for this distribution is 1 over lambda. So maybe I should compute the sample mean and flip it over. It's one idea. We're going to have a lot of ideas. So here's an idea. Estimate lambda with 1 over x bar, just because I kind of matched the means and then I solved for lambda. I don't know. That's an idea. So the first idea was kind of silly with the histogram, which is not so silly at first, but it's going to really be affected by how you bend the histogram. This one is what I call a common sense estimator. It may not be common sense to you now, but because you're just getting started. But I think it's like a very intuitive way to go for lambda. But I can also estimate lambda with the number 11. I could just say 11. No, I don't want to, 11. And that's my estimator. I didn't even look at the data, so it's probably not a good estimator. The point of this chapter is for us to figure out good properties of estimators so that we know how to construct them. So we're not going to have any kinds of algorithms or formulas for actually, or even formalism for coming up with estimators in this chapter. That's coming in the next chapter. And it might be a little frustrating that you don't have that yet. But we're going to derive methods for coming up with estimators based on what we'd like them to be, like how good they should be. So this is the chapter where we talk about qualities of estimators so that in the next chapter we can figure out how to actually find them. So there's going to be a lot of problems where I'll give you an estimator and say, show it has this property, show it has this property, but you still won't know how to come up with them. Okay, so so now I'll actually start writing things. Sorry, there was a lot of conversation there. It wasn't maybe so good for note taking. Our generic parameter is always going to be a theta. And this can be one-dimensional or higher. So for example, theta could be a lambda in the exponential distribution, or theta could be the alpha and beta from the gamma distribution. And for the Weibull, we have 3 parameters. So it's just a generic parameter and possibly vector valued. So I really want to stress the dependence of the PDFs on the parameter. So from now on, I'm going to write the PDFs like this. I'm going to use f of x and then a semicolon theta. And I'll tell you why I'm using the semicolon and why you don't have to use it. I'm using a semicolon, first of all, instead of a comma, because we're going to look at joint PDFs, so we're going to want to look at an f of x1 through xn. And so I want the semicolon to sort of like show that that's a different part of this. Now, I know some of you are going to maybe want to put a line there, and that's okay, but I'm not going to do that. So you might see this. There's nothing wrong with it, and go ahead and use it if you want, but I'm not going to, because I think it's a loaded statement. If you know about conditional probabilities, it kind of looks like a conditional PDF given theta, which it kind of is, but this starts to look like Bayesian statistics, and which is not what this course is about. But in Bayesian statistics, you treat the parameters as random variables. So you do talk about conditional probabilities where the x's given the thetas and the thetas given the x's. And I think seeing that line there makes me think conditional probability. But it's certainly used a lot, and you're welcome to use it. Okay, so the semicolon is also going to help us distinguish, if we have a couple of parameters like a mu and sigma squared. Okay, so we're going to write an estimator. We're going to denote an estimator, which is different than an estimate. For theta is going to be denoted with a theta hat, or possibly in a case where you're doing a problem where you're coming up with several estimators and maybe comparing them, maybe a theta 1 hat and a theta 2 hat, something like that. And I use the terminology estimator as opposed to estimate. So an estimator, I'm going to stop saying it like that soon, is a random variable. It is a random quantity. So suppose we want to, actually, let me make this an example. So I have a random sample, x1 through xn, iid, and I haven't used this notation yet, so check this out. I'm going to put a mu and a sigma squared here, and I didn't put the n, so this is not a normal distribution. This is just a way to write out a random sample from any distribution with mean mu and variance sigma squared. Could be exponential, where mu is 1 over lambda and sigma squared is 1 over lambda squared. Could be Poisson, where mu is lambda and sigma squared is also lambda. So I didn't write any distribution name. So we might consider an estimator of mu is mu hat. We can take the actual mean. That is a random variable. I made that nice and capital. Again, my small x's are kind of curly. That is an estimator as opposed to an estimate. An estimate is when you actually have the numbers. We're not going to talk about these very much. So an estimate is the actual numerical value, and unfortunately, it's also called mu hat, but it's actually a number, not a random variable, whereas this guy is a random variable, So what we care about is the random stuff, because we're trying to give prescriptions for other people to do statistics with. So we're trying to say, you should use this statistic as your estimator because I worked out the probability that it is this close to the thing you want. And once you have numbers, there's no more probability. Your sample mean in the numerical case is either equal to the true mean of the distribution or it's not. There's no probability there. So we want to talk about them while they're still random variables. So again, we can say things like, if you were to use this versus this estimator, you're going to be this much closer with probability 0.8. We want to make probabilistic statements. So estimator is random. I'm not going to get on you about this. It's not really going to come up. If you call it an estimate, that's no big deal, but there is a difference. Okay, so click for up there. So I already said that theta is a generic parameter, and sometimes we're going to want to estimate, you know what, let me bring this all down. Oops. Okay, so here is the setup for going forward. Our generic parameter is going to be called theta. We're going to start writing our PDFs with an expanded notation to really emphasize the dependence on theta. And then sometimes we want to estimate not theta, but a function of theta. So if you think it's a good idea to estimate a mu using x bar, what if someone wanted you to estimate mu squared? Do you just use x bar squared? Maybe. That's a really good idea. That's a common sense kind of thing. But we got to talk about the properties that we want our estimators to have. And actually, that will fail some kind of good properties that we might want. Sometimes we want to estimate a function of a parameter. And our generic function of theta to be estimated is going to be denoted by a tau of theta. So for example, estimate tau of theta equals theta squared. Again, the really obvious thing to do is take your estimator of theta and square it, but that may not be the best thing to do. But we're going to use a tau of theta to denote a generic function. And so we're going to estimate it with tau of theta hat. And that is a random variable. and it may or may not equal tau of inside theta hat. Okay, so notation. Here's a really important definition going forward, and that is the idea of an unbiased estimator. This is a good quality that an estimator should have. So here is a definition for you. And yeah, it makes more sense for me to do it with the general tau, but I'm going to start with just a theta because I think it's a little easier to absorb the notation and read. So we say that an estimator, theta hat of theta, is an unbiased estimator for theta, or more simply, we say it's unbiased for theta if. So we just talked about estimators being random variables. So they have distributions, they have means, and they have variances. And so the definition of an unbiased estimator is that the expected value of theta hat has to be theta. And that seems like a really nice property. You know, it says on average, you'll be right if you use this. So this really should have been the definition because it's more general, but I just wanted to write that down a little cleaner first. I just want to talk about it for tau of theta. An estimator tau of theta hat of tau of theta is an unbiased estimator if its expected value is the thing you want. So let's look at our first example, which is a super important example because you will be reusing this result, which is, it's really short, but we're going to use it every day in math stat. So here is an example. Suppose I have x1 through xn IID from some distribution with mean mu and variance sigma squared. And I'm not going to say what distribution. So we're going to consider estimating mu with x bar. So I'm going to say mu hat is x bar. You could say mu hat is 11, la 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 la, or something else. And then we want to compare who has a better estimator. And again, that's the point of this chapter. What does better mean? So we now have one nice property for estimation, for estimators, and that is that this is always an unbiased estimator of mu. So I didn't even have to write down a distribution, but if you look at the expected value of this estimator, that is the expected value of x bar. That is the expected value of 1 over n, the sum as I goes from 1 to n of the xi. And then we can use the linear operator property of expectation to pull the 1 over n out and pull the sum out. And this is 1 over n, the sum as I goes from 1 to n of the expected value of xi. Now they're IID, so they all have the same PDF and they all have the same mean and the same variance. So this is going to be 1 over n, the sum as I goes from 1 to n of mu. And then that doesn't even depend on I. So that's a mu plus a mu plus a mu plus a mu n times. So 1 over n times mu, and we get mu. So without even knowing the distribution, we have seen that the sample mean is always an unbiased estimator of the true mean. It's a really good thing. The true or population or distribution mean, mu. Okay, so our first unbiased estimator, and it's going to work for all distributions. Well, something else I want to look at before talking about bias is the spread of this estimator. Because if you get a sample of size n and compute the average, the sample mean, and actually do it numerically, and then you get another random sample out of the overall population and you compute the mean, and get another one, you'll get different numbers. And unbiasedness says that, so I'm going to draw another one of my lines, right? So the x's represent various x bars that were recorded. You're going to get something, 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 but on average, you're going to be right. And it may or may not have a nice bell curve shape. Although there is a famous theorem coming up called the central limit theorem that says in the limit, almost all distributions for x bar will turn into a bell, a normal distribution, even if you start with something very not normal, an exponential, say. So it's unbiased in the sense that it is kind of centered around mu. And my question to you, or not my question, my statement to you is unbiasedness is not the be-all, end-all property of estimators that people would have you think, that even I would have you think, because I constantly talk about unbiasedness. Because you will only get, usually, one sample. And so you'll only get one number. So you won't get to see all of these guys. So you would hope that whatever you see is close to this mean mu. And maybe you would prefer a different estimator. So this is, let's say, the PDF for a mu1 hat, like one kind of estimator, probably X bar. But if I had another estimator, mu2 hat, its PDF might be like this, which is kind of not centered in the right place. That looks biased, but way more predictable. Small variance, which is the next big property we want for estimators. So unbiasedness is not the be-all, end-all. Predictability is also kind of important. And this one is going to most of the time be closer to this, the true mean, than your other estimator. Wouldn't you like both? Wouldn't you like the minimum variance unbiased estimator that you can guarantee no one anywhere can do better than? The UMVU, and it's coming. So now we know some of those words in the acronym. Okay, so unbiasedness is, again, not everything, but it certainly is a lot. So let's look at the, while we're looking at the sample mean, let's look at the variance. We can also do that without a specific distribution. Note that the variance of x bar, the sample mean, is 1 over n, the sum as I goes from 1 to n of the xi. We can pull constants out of variances, but they come out squared. And we can't generally pull sums out. We talked about the variance of x plus y being the variance of x plus the variance of y minus 2 times a covariance term. But if x and y are independent, the covariance disappears and is 0. So we can pull the sum out in the case of independence. And I'm assuming we're still talking about the random sample, the IID things. So independent only, and you can pull the sum out. And then if we have an IID sample, they all have the same variance. So we've got 1 over n squared, the sum as I goes from 1 to n of sigma squared. And so I have n of those, right? So this is 1 over n squared times n times sigma squared. It is sigma squared over n, where sigma squared is the original variance for the individual x's from the distribution. So the variance of x bar is smaller than the original variance, which makes a lot of sense. You know, a lot of you are teaching right now Calc 1 or Calc 2, and it's on the first exam, you're going to see a lot of variability in scores. You're going to see probably a 0, unfortunately, and 100 or 103 if you give bonus points, and all kinds of things in between. But if instead of listing all of the test scores for all Calc 1 students, if you just went into each recitation section and gave an average, those aren't going to be nearly as variable. Like you'd be hard pressed to get an average of 0 and an average of 100. And that's what we're seeing here. The sample mean has smaller variability than the individual values. And as n gets larger, it goes way, way down. It's sort of, you know, it's on average, it is mu, the true mean. So the distribution of x bar, it doesn't necessarily have to have this shape, but it's something centered at mu. And as n gets larger, it gets closer and closer and closer. And yeah, in the limit, x bar is going to approach mu. But we don't really know what that means, because x bar is a random variable and mu is a constant. So a big part of this chapter, and starting on Monday, is going to be talking about convergence for sequences of random variables, because they're not numbers, they're wannabe numbers. And so there's many ways to talk about random variables converging, and they all have to involve probability somehow. Like the probability that this gets close to this, or maybe look at the expected value of the sequence of random variables. Those are just numbers, so we could talk about those going to mu. We're going to have all different types of convergence for random sequences. So I will make sense out of, don't write this down, or you can do what you want, I guess, but I'm going to make some sense out of this statement. Like, what does that even mean? If you write it down, put the question mark so you don't come back later and think that was just an epsilon kind of thing. Because again, random, moving around, fixed. Okay, so small variance is another property we want. We would love our estimators to be unbiased and have small variance. Uniformly, minimum variance, unbiased estimator. We're headed there. It sounds like we should be there like next week, but we won't. Okay, so small variance is a good thing. Small variance of an estimator is a good thing. Because if I only get one sample, I only get one number, and hopefully it doesn't swing wildly around the number I'm trying to, determine. Okay, but if we have some bias, then, well, if it's not unbiased, then it's biased. So I want to define for you the bias of an estimator. So here is a definition. I'm just going to do this with theta. It would also work for a tau of theta. The bias of an estimator, theta hat of theta. So I'm going to both put a notation and a definition. We're not going to see this notation again after today, so it's not that important. Usually a B of theta hat because it's a property of the estimator. And it's defined to be the expected value of your estimator minus the thing you're trying to estimate. So if you have an unbiased estimator, then this expectation is this, and you get a bias of 0. Okay, so you might want to put that the other way. Like, why don't we subtract the other way? It really doesn't matter because it only ever comes up in statistics squared. And I have another definition for you. And this is that of the mean squared error of an estimator. So I'm going to regret this because it takes so long to reshare the screen, but I'm trying to make an effort to come back to you. If your estimator, if you're trying to estimate, so here's a number line, and you're trying to estimate some number, and you have a random variable which sometimes falls here, sometimes falls here, sometimes. If it has some bias, then you might care about how far away it is from the true thing. And so this is known as, well, depending on how you compute it, we're going to look at the distance between the estimator and the thing we're trying to estimate, and that's a random variable. We're going to square it so it's nice and positive and mathematically convenient rather than use an absolute value. And then we're going to take the expected value of that. So that's known as the mean squared error, which is our next definition. So I'm going to define the mean squared, I guess people don't usually put a hyphen there, error, which is affectionately referred to as the MSE of an estimator theta hat of theta is, we're going to write MSE. It's a property of the estimator, so MSE of theta hat, and it's defined, that's what that colon is before the equal sign. It's defined to be the expected squared difference between the estimator and the thing you're trying to estimate. So again, this guy is a random variable, and this guy is a number. And if you have an unbiased estimator, then, so if the expected value of theta hat is theta, dang it, I keep thinking I go to 250. I'll have another minute. If the expected value, I have it I have this sticky note in front of me every day. But if it's unbiased, then what you're seeing here is a random variable minus its mean. So this is a variance term. The mean squared error of theta hat is actually the variance of the random variable theta hat, because if you want to compute that variance, you'll subtract its mean, right? And if it's unbiased, that's theta. You'll square it and compute the expected value. So if the estimator is biased, then mean squared error means something a little different. But it's kind of more interesting if, yeah, I won't get to show that now. So here is a number line. Here is the true unknown theta. And if your estimator of theta has some kind of distribution that's biased, then I don't care that much about how much spread there is in this distribution. I don't really care about the variance of this as much as I care about how far apart these guys are, which is what mean squared error is in the case of a biased estimator. You know, it's a squared error, or how off we are, and it's a mean. So next time, we're going to relate the MSE and variance if for a biased estimator, and then we're going to start estimating. Thank you.